Hey everybody, so today we're going to be learning about rational and irrational numbers. We're going to go through and determine on which numbers are rational, which numbers are irrational. We're also going to add in there some what are not real numbers. I'm just going to give you a little preview of that. So today with the irrational and rational numbers. You started learning about this in probably fifth grade, moved on to sixth and seventh grade. You learned a little bit more. And of course, in eighth grade, just like everything else, we're going to get more in depth and put a little bit more understanding on what rational and irrational numbers are. So, when we do this, we're going to talk about positive solutions first. Just like when you were little, we learned about positive numbers first. So, could 8 be a solution to this? Why or why not? So, let's go ahead and take a look at this. Could 8 be a solution to this? So, that means that we need to know about what is going on with our squares. Now, we have learned about this year a little bit, where we were learning about square roots. And if you square root a square, these kind of cancel each other out. And so that's how we would be able to find our square root of 49. But their question is can 8 be a solution to this? Is 8 equal to x? Well, let's go ahead and find that out. So if we were to take 8 times 8, what does it equal? Well, we know that it does not equal 49. This is actually equal to 64. I ate and I ate till I was sick on the floor. 8 times 8 is 64. Um, just a fun little thing for you to remember that. So, what is our x equal to? Well, we in eighth grade should know by now that 7 times 7 is equal to 49. So, x is actually equal to 7. So, that's our positive solution. Why are we saying positive solution? Well, we're saying positive solution because while 7 times 7 is 49, we could also say negative 7 times negative 7 is also equal to 49. Why? Because a negative times a negative is a positive. So it would actually equal the same thing. Let's clear this. And what we're going to do now is you're going to go ahead and you are going to be finding me some positive solutions. You're going to tell me why or how you found that. So I want you guys to take a few minutes and you're going to find the solutions to these. You might be right, you might be wrong, but I want you guys to try and then we're going to go over what our answer is. Let's see if you can figure this out, put some thought process into what you already know and where it could be leading you. So go ahead and pause and answer these 4 questions, and I'll be right back with you. All right, so you guys have had a few minutes to work these out. So x squared is equal to 36. Now, mind you, they are wanting to know about positive solutions. Positive solutions. Not, I know there's a positive and a negative for each one of these, but again, they're only looking at the positive. So let's see. What multiplied by itself could equal to be 36? Well, again, if we were to go ahead and do 6 times 6, this is equal to 36. I noticed that because I know that you guys know what your basic numbers multiplied by themselves are. 1 times 1 is 1, 2 times 2 is 2, 2 times 2 is 4. So just going on like that. So if we're going to do that, this is the square root. Okay, square root. This is how we're finding this. I know that I'm asking you guys what times what is equal to this. Well, just like we're square rooting this x, we are also going to square root this number over here. So what I want you guys to really think about is breaking this number down into parts, because this is a 9, this is a 4, So could we find the square root of 9? This is the same thing as saying if it was equal to square root of 9 divided by the square root of 4. This is the same thing. It's equal to each other. Okay? So what times what equals 9? Well, I know that 3 times 3 is equal to 9. So the square root of 9 is 3. All right, square root of 4. So what times what is equal to 4? That would be a 2. So the square root of 9/4 is equal to 3/2. And if you're not sure about that, we could go ahead down here in our corner, do 3/2 times 3/2. All right, when we multiply fractions, we know that we multiply straight across, and 3 times 3 is equal to 9, and 2 times 2 is equal to 4. And this matches up with this over here. All right, let's clear this screen up. So I'm just going to put it back on here. 6 times 6 is equal to 36. And the square root of 9/4 is 3/2. All right, so could we find the square root of 1/4? What times itself is going to be equal to 1? I know that seems kind of like a crazy question. Some people are probably thinking like half, but a half times a half is not going to equal 1. It's going to equal 0.25. So it doesn't really work out that way. So 1 times 1, actually, 1 times 1 is equal to 1. So the square root of 1 is 1. Where down here, I need to find 4. So what times itself is equal to 4? Well, that would be 2 times 2. So the square root of 1/4 is actually 1/2, which makes sense because earlier when we were talking about what could be the square root of 1, and we were talking about if I was to take 1/2 or 0.5 times 1/2, that equals 1/4. So now we're going to look at square root of 49/25. Well, 49, we know what that is. Figured that out earlier. Square root of 49 is 7. And the square root of 25 is going to be 5 because 5 times 5 is 25. So when you're looking at this, you could say, I noticed that, especially for here, I noticed that the square root of 9 is 3 and the square root of 4 is 2. So let's clear our screen. All right, 3 squares. This is where we're going to get into some really interesting things. We're going to be doing some discovery. So what we're doing here is we're going to find 3 squares in these different boxes. There are 3 vertices in each 2x2 grid. Okay. And so I want you guys to draw 3 squares of different sizes with the vertices aligned to the vertices of the grid. So when we're talking about that, like, yeah, these actually are touching the vertices in the grid. The problem is that this is a rectangle. Now, all squares are rectangles, but not all rectangles are squares. This is not a square. This is not a square. So that doesn't actually equal out to being square when it's asking you to draw 3 squares. This is not an actual option. Now, this looks like a square, but doesn't have the vertices aligned to the grid. So Is it a square? Yeah, it's tilted on its axis. The problem is, again, is that we're not using our vertices. Our vertices are here, 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 here. So it's not using these. We're using partials in between. So that's not what they want you to do either. So these are what not to do. What not to do. What is that? Beep. Not. Not to do. There we go. Um, so we're going to so we're going to share your ideas in a few minutes. So go ahead and pause and work on that. All right. So what are some of your ideas? Well, one idea, of course, would be this right here, this big square that we have here. This would be one square. All right. So let's go ahead and do our second square. We can do another square in green. I'm going to choose this square right here. So we have one square, two squares, but the problem is that they want us to find a third square. So, let's see. Let's put these back. We have this big square. We have this little square. And next up, we're going to be finding our fourth square. We're going to do this one in blue. Now, it wants us to use our vertices. That means that we have to use any of these corners. We have to use that for vertices for our new square. So what we're going to do is we're actually going to take this. We're going to draw. You know that I'm an amazing artist. So let's see if we can get this. We're going to draw like this. Let's see. We're going to go back. We're going to erase because I'm amazing at drawing. Let's see. Beep, beep. All right, let's try this again. We're going to draw here to here to here to here. Yes, you can make fun of me. No, I don't care. I know that I'm amazing at this. I know you guys are super jealous. So, all right. So what we're going to do now is this not only uses our vertices of our 2x2 square, but it also uses our vertices for this. So we're going to figure out some different information. They want to know, now that we've drawn our three different sizes with our vertices aligned to our vertices of the grid, for each square, they want us to label the area, label the side length, and write an equation that shows the relationship between the side length and the area. All right, so first thing that we're going to do is we're going to find our area. Let's do our big square first. So we're going to be finding our area. So area equals. We know that our area is our length times our width, or since we're talking about a square, it's going to be side length times side length. Well, our side is a 2x2, so area is going to be 2 times 2 is equal to 4, which makes sense because 2 squared is 4. So our side length is equal to 2. And then they want us to write an equation that shows the relationship between the side length and the area. The side length and the area. Well, we did come up with area is 2 times 2 is equal to 4, and our side length is 2. So what we're going to do is we're going to say 2 squared is equal to 4. So this is our equation for this. So now what we're going to do is we're going to do the same thing with our green square over here. So our area. So let's take a look for our area. What is our side length? Our side length here is 1 and our other side length is 1. So this is 1 times 1 is equal to 1. Our side length is equal, to 1. And our equation for this would be 1 squared is equal to 1. All right, so over here, this is a little different. So we're working with our blue square now that is drawn amazingly because, I'm an amazing drawer, artist. So area is equal to what? What is our area equal to? Well, we're going to have to figure that out a little bit. So if I have this big 2 by 2 grid, I need to find the area just inside this blue square. I just need to find the area of this blue square right here. So to do that, I need to get rid of the other sections that are here. So this section needs to be taken off and this section needs to be taken off. All these pink areas need to be taken away. So we know that the whole 2 by 2 grid, we know that that is equal to a 4. So if we have these cut in half, these pinks, so this is a half. So I have 1/2 here. I have 1/2 here, 1/2, and 1/2. So if I have 1, 2, 3, 4, 4/2, which would look like this, 4 over 2, 4 divided by 2 or 4/2 is equal to 2. So if I have 2 taken away, my whole area of the whole grid is 4. I'm subtracting 2 away from that. So the area of my blue is actually also a 2. So my area of my blue square is going to be equal to a 2. So now we're going to be we need to find our side length and we need to find our equation. So what we're going to do is we're going to try and figure this out. So what we're going to have to do is we're going to have to look at this a little bit different because we don't actually know what our measurement is right now at this moment. We do know, though, is our area here is 2. Well, our area here was 1, and that meant that if we were to square 1, we ended up with other 1. So square root of 1 is 1. Here, our area was 4. Well, if we square rooted 4, this is how we got 2. So for our side length here, we're going to have to write this actually as the square root of 2. Do we know exactly what the square root of 2 is? Now we know that 1 times 1 is 1, and we know that 2 times 2 is 2. So we don't actually know what our square root of 2 is at this moment. So we might have to take the time to find this. But what we do know is that with our area being 2, we know that the square root of 2 squared is going to be equal to 2. So the reason that we're saying that is because when something is squared, when you square root it, these two cancel each other out. And so, of course, 2 is equal to 2. So that's how that works. So here it is drawn, of course, better. So our first square was the area 4 by 4 and our side length of equaling 2. Our second one was our 1 by 1 and its area was equal to 1, and our side length was also equal to 1. And here with our area of 2, and we said that our side length was the square root of 2. So now we're going to start looking for a solution. When we're looking for a solution, what we're going to do is we're going to get a little bit more in depth on, can we find what the square root of 2 is? So reminder, 1.5 is equivalent to 3 halves. So you're going to begin working on your own on section 3.3, looking for a solution. Which of these numbers are a solution to x squared is equal to 2? I'm going to give you guys about 2 minutes to try and figure this out. So now that you've had a few minutes, what we're going to do is we're going to see if any of these numbers, when they're squared, if they are equal to 2. So first we have 1 times 1. Well, 1 times 1 is equal to 1. So this is not a solution. 1 half, let's see if we take 1 half times 1 half. Well, 1 times 1 is equal to 1, and 2 times 2 is equal to 4. 1/4 is definitely not a solution to 2. All right, 3 halves. All right, 3 halves. So we have 3 over 2 is times 3 over 2 is equal to 6 over 4. 6 divided by 4. That's not really good. 6 times 4, that's still going to be not a solution. We're getting a little bit closer. So let's see. 7/5 times 7/5. All right, so 7 times 7 is 49, and 5 times 5 is 25. This is actually really close to 2, because if we were to take this 49 and we were to put it actually up to a 50, if we rounded it, 50 divided by 25 is equal to 2, but 49/25 is not equal to 2. So it's close, but it's not exact. So that doesn't really work out. So which of these numbers are a solution to the equation x squared is equal to 2? None. None of these are actually a solution. Sad. Right. So before we go on with our next part, let's talk about a rational number. A rational number, A divided by B. Okay, a fraction or its opposite. Remember, we can always write a fraction in form of A divided by B, where A and B are whole numbers and B is not a 0. This is super important. You cannot divide by 0. We've talked about this before. That's how we got our undefined slope. Um, and they can be positive or negative. Rational numbers can be positive or negative. One of the main things that I do want you guys to notice here is that in the word rational, you have that word ratio. Fractions are a ratio, so that makes perfect sense. A rational number is always going to be a ratio. It can be made into a ratio. That is how we know what rational numbers are. All right, because fractions and ratios are closely related, ideas, fractions, and their opposites are called rational numbers. Here are some examples of rational numbers. So we have 7/4, we have 0, 6/3. If you notice, we have squares on there. Now, mind you, they're perfect squares. So the square root of 9 is going to be 3. So, of course, 3 is a rational number. If you make that into a fraction, it's 3 over 1. You also have over here, you have the negative, square of 16 over 100. Well, 16 is a perfect square. This is going to be equal to -4 over 100. So this is actually -1/25. But again, it is a fraction. So it is going to be a rational number. Now, notice these are perfect squares. It has to be a perfect square for it to be a rational number. So let's look for the square root of 2. Let's look for the square root of 2. Can we find some more numbers? Can we look in and see if we could find a number that is actually the square root of 2? So I want you guys, so let's see, rational number, a fraction or its opposite, examples 9/8 and -9/8. Terminating decimals like 0.7 is equal to 7/10. Um, a rational number is a fraction and its opposite. We've talked about this. So let's find some rational numbers that are close to the square root of 2. And can you find a rational number that is exactly the square root of 2? Exactly the square root of 2. So pause here and figure out what we could do and what numbers we might be able to find that are exactly the square root of 2. All right, so let's see. One of the ones that I could think of would be 10, 10, 10 squared over 7 squared. So 10 squared is 100 and 7 squared is 49. So just like the one that we had earlier, where it was 49 over 25, if we took our 49 and moved it up just a little to 50, it was really close, and we had 50 over 25, that would be equal to 2. Well, here we have 100 over 49. So again, if we happen to put this 49 as a 50, then it would be 100 over 50, which would be equal to 2. So again, we are close, but not exactly. So did anybody find anything that is equal to exactly the square root of 2? No, because there is no number that exists for it to be uh, exact, because it is an irrational number. Irrational number. So let's go ahead and talk about irrational numbers. So here we go. We have the real number system. We're not going to look over here at the not real numbers yet. We're going to just go to look over here at the real number system. So we have rational numbers and we have irrational numbers. Yeah, rational and we have irrational. So, rational numbers, they actually start with our counting numbers. Counting numbers are numbers that we first learned how to count with. We've gone over this a couple of times. So, 1, 2, 3, blah, blah, blah. All right. Whole numbers. Now, whole numbers are just like counting numbers, except for they give you a 0. So, it'd be 0, 1, 2, 3, etc., etc., etc. All right, so now this is where integers come into place. Integers are a little bit different. So integers are actually fractions. They could be a fraction. So if I was to take like 10 over 5, because 10 divided by 5 is 2. So that this right here could be an integer. Integers are whole numbers and their opposites. And of course, fractions that are equal to whole numbers or their opposites. So negative 3 and positive 3 are both integers. Negative 2 and positive 2. So, next up, we have rational numbers. All of these, of course, are rational numbers. Our counting numbers, our whole numbers, our integers are all rational numbers. So, what else are rational numbers? Well, rational numbers are actually not just these, but they also add in any terminating decimals or any repeating decimals. So a terminating decimal would be like 0.25. 0.25 is equal to 1/4. Um, so this is actually a rational number. Another rational number. So if we had zero point 0.3 repeating, zero point 0.3 repeating is equal to 1/3. So that is a rational number. So any of these, if you had 0.75 or negative 0.75, is also a rational number because, again, just like integers, it's any number um, that is a terminating decimal or repeating decimal can be made into a fraction and its opposite. So all of these are rational numbers, even if you were to have like negative 2/3 rational number. So, next up, we're going to be going over irrational numbers. Irrational numbers are numbers that don't repeat, they don't terminate. It's more of like it goes on and on and on and on forever. So, one of those numbers that I know that you guys are going to know, one of the main ones that are irrational would be pi. Pi is an irrational number. We do round it to 3.14 or 22/7, but it is actually an irrational number. It goes on forever. We just had Pi Day not too long ago, so you know that that's a number that just goes on forever. So if you see a number like 2.37614 dot dot, this is actually called an ellipse, and it means that it just keeps going on. It doesn't repeat. This is an irrational number. Um, Other irrational numbers that are good to look at are square roots of non perfect squares. Square roots of non perfect square. So here, over here at our rational numbers, if I said the square root of 9, square root of 9 is equal to 3. That is a rational number. However, the square root of, say, 10, there's not a number when multiplied by each other that equals 10 exactly. Is there numbers that come close? Yes. But just like we found out, the square root of 2, 2 is not a perfect square. So that means that this is an irrational number, and that's the reason why. So let's go ahead just to give you a brief of not real numbers. Not real numbers can be broken down for right now, just to give you a quick, as any number divided by 0. We learned this when we were working on slope, and this ends up being our undefined slope. Uh, so this is a not real number. Another not real number, so negative 4. So the square root of 4 is 2, but the square root of negative 4, that's not a real number. Now, if we had over here, if we said negative square root 4, this is actually equal to negative 2. This is a rational number. This number isn't even real. This is not happening. So let's see. An irrational number is a number that is not rational, obviously. It is not a fraction or its opposite. The square root of a whole number is either a whole number or irrational. So the square root of 10, the square root of 67, etc., are all irrational. They're close to being perfect squares because the square root of 9 is a perfect square, which would be rational, and the square root of 64 is 8. So that one would also be rational too. But 67 is close, but not exactly. These are irrational because the square root of any non-perfect square is going to be irrational. So today's goal, I know what a rational number is and can give an example, and I know what an irrational number is and I can give an example.